Well, a question comes up. When we're working with a cell, we go and we look up those standard reduction potentials, but how did those values even come into existence? And if you think back, we realize that Celsius is a temperature scale that starts at 0 when water freezes. Somebody picked water as a standard, and we have a similar situation here. We have what is called the Standard Hydrogen Electrode. She who must be obeyed. Okay, anyway, what we did is pick a particular reaction to serve as the standard. That 2 hydrogen ions with 2 electrons will make hydrogen diatomically, okay? And that would be set as a 0. This sometimes confuses people and they think, well, then it just won't happen. Well, no, remember, this is just a half reaction. It's always going to depend on what is paired with it. The other thing you might notice from this is that we mentioned electrode. We'd been talking about anodes and cathodes. We hadn't mentioned electrodes. Electrode is the more generic term. Anodes and cathodes are both electrodes. So when we have one of these standard hydrogen electrodes in a circuit, it could serve as either an anode, in which case, if you're writing the cell description, it would appear on the left before the double bars, or it can serve as a cathode and be on the right. The platinum itself is not going to be affected. It just stays there as is. You'll notice it's a little more complicated. We have 2 of these, but the platinum is just a mechanism for making sure that the electrons can be transferred, because electrons don't transfer very well through a gas, let's face it. But through a solid metal, they go right nicely. So it is just a conveyor belt for these electrons to move along. The other thing that we might notice about batteries is sometimes they go dead. Why does that happen? Well, we know that reactions stop when one of the reactants is completely consumed. And now, as it turns out, with your batteries, it happens before that. It stops before everything is completely gone. And that is because the cell potential is determined by the concentrations of the reactants and products. Oh dear. Well, you know, that had to come into existence because we were talking about delta G being involved, right? The Gibbs free energy. So we know that something has to give. When things are getting close to completion, they aren't going to go as quickly. So we have that happening within a cell. Now, the nice thing about a battery is that it travels along and does not decrease very quickly until it is almost completely done, and then it just like falls off the cliff, okay? So if your equipment is made so that anything over 2 volts will make it operate, you are going to get over 90% of the reactants to react before your battery will quit. And here's the formula that we're going to end up using, which we'll explain that formula a little more later, because, whoa, where did all this stuff come from? I mean, okay. The actual voltage that you see is based on the perfect voltage that it could have. It will be reduced by something. What's it reduced by? Oh, our favorite gas law constant, the temperature, the natural log of Q. Q is back again. Remember, Q is telling you about the actual equilibrium, not K, the equilibrium constant, but what's the actual number at the time. And then we have our new friends, NF down here. Well, N's old friend, but F is Faraday's constant, is new to us. And it turns out that since most of the time we're trying to stay at a particular temperature, 25 degrees Celsius, if we set the T to be 298 Kelvin, which is 25 degrees Celsius, and we switch to base 10 because we're more used to using base 10 instead of natural logs, that this will turn out to be our formula. So if we can keep it at that standard temperature, the formula gets much easier to deal with. And then we'll have instead of a natural log, we'll have a log base 10 of Q. But this helps show you why the voltage will depend on the temperature. This is not something we worry about a lot in California, but if you lived in Minnesota, you'd be a little more concerned about this. This one is telling you if the battery gets too hot, it's going to degrade the performance. So what's up with me talking about Minnesota? Well, if you'll recall, the kinetics is changed by the temperature. The kinetics slows down at low temperature. So we have two different things that are going to ruin our good time with electric batteries.